Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about heating curves, specifically the heating curve of water. So what you need to know about water is that it has different specific heats depending if it's solid, liquid, or water. So when it's ice, the specific heat is 2.092. When it's liquid water, 4.184. This is the number that we're probably kind of used to from the last couple videos. But if it's in the gas phase, if it's steam, the specific heat of water is going to be 1.841. Now, whenever we use specific heat, we're using that Q equals MC delta T equation. However, when we melt things or when we vaporize things, we're going to do it in a little bit different manner. So let's get into the video, okay? We're going to first start off by talking about what exactly is a heating curve. Basically, what a heating curve is we're following the temperature as we add heat. Okay, so the x-axis is going to be the amount of heat added, and the y-axis is going to be temperature. Okay, and we're doing the heating curve of water. So we're going to start down here at a random negative temperature, let's say around negative 40 degrees Celsius. And at negative 40 degrees Celsius, we know that water is in the ice form. Okay, but as we start to heat, okay, as we move along the x-axis, the temperature is going to start to increase, okay, until it gets to the melting point of water, okay? And the melting point of water is going to be 0 degrees Celsius. This is when water freezes, okay, if it's going from liquid to solid, or when it melts, when it goes from solid to liquid. Since we started with a solid, when we get to 0 degrees, this is the point in which it starts to melt. And what's going to happen as you continually add heat, the temperature is not going to change. So it's going to be kind of like a horizontal line. And we call this area of the heating curve, we call this the area in which it melts. We call it the enthalpy of fusion. So the enthalpy change, FUS, okay? So enthalpy change of fusion basically means if this is the amount of energy that is required to melt ice. In this case, it requires 6.008 kilojoules of energy that needed to be supplied per mole of ice that we have. Okay. Now, when the ice is done melting, okay, and we get to this point, and as we continue to add the heat, if it's all melted, it's all liquid water now the temperature is going to start to increase again, okay, until we get to the boiling point of water. And the boiling point of water is 100 degrees Celsius, okay? So when we get to this point, once again, as we add the heat, okay, it's going to stay the same temperature, okay? And instead of calling this the enthalpy of fusion, which is melting, we call it the enthalpy change of vaporization. And the enthalpy of change of vaporization is 40.67. It is so much higher than the enthalpy of fusion. And that is because to break the intermolecular forces, like if this is a solid, to break the intermolecular forces to turn it into a liquid, you only have to break them enough, okay, so that the molecules can start sliding past each other. In this case, it requires around 6 kilojoules per mole of water. Now, to go from a liquid, which is like this, to a gas, you're breaking a lot of intermolecular forces. You're breaking them so when it turns into a gas, there's absolutely no attraction between the gas molecules, and that there's like 99.9% empty space in between the molecules. So it's going to require a lot more energy to do that than just enough to pull them apart so that they could slide past each other. About 7 times more, okay, because 6 times 7 is 42, and I'm about 41 here. So almost 7 times more the energy to go from liquid to gas than solid to liquid, if that makes sense to you, okay? So the enthalpy of vaporization, this line technically should be like 7 times longer than this space, okay? But I want to make sure it was visible for everybody to see down here, so I made this this particular size, okay? So now when we get all of the liquid into a gas, we then can heat that gas up, okay, to a higher temperature. Let's say like, around 130 degrees Celsius, something like that, okay? Any temperature that's above 100 degrees, okay? So when we're dealing with the heating curve, okay, wherever the line has slope, okay, that's when we have to use Q equals MC delta T. Okay, so I'm going to use Q equals MC delta T here. I'm going to use Q equals MC delta T for this part, and I'm going to use Q equals MC delta T for this part. However, the specific heat that you use is a particular number. So when it is ice down here, the C that I have to use is the 2.092 number. The specific heat here, when it's liquid water, is going to be the 4.184 number. And the C that I'm going to use here when it's steam is going to be the 1.841 number. Likewise, when I'm in the horizontal part of the heating curve, I'm going to use this 6.008 number. And remember, that's going to be in kilojoules per mole. When I'm down here, it's in joules per gram degree Celsius. So I probably should put my units in here. Joules per gram degree Celsius. And the same thing for heat of vaporization. It's in a kilojoule unit. So that's going to cause us some issues when we get to some of our problems, because some of the units are going to be in joules and some of them are going to be kilojoules, and you're going to see where that all plays out. Okay, so let's go ahead and get into a couple practice problems just as a warm-up before we get to our big problem at the end. And if you can get to the big problem at the end, I would say that you are a pro at using the heating curve. Any portion of it, I would consider you a pro. Okay, so the first question is going to be, what if I have some liquid water? I'm not liquid water. Let's say I have some solid water, okay, and I wanted to turn it in to liquid water, okay. Now the amount that I have is going to be 15 grams, and we are at 0 degrees Celsius. So basically, we're at this part of the heating curve, and I want to melt that ice, okay. So I want to turn it from a solid to a liquid, because right here the liquid water, the water is a solid, and over here the water is a liquid. Okay, so what we're going to have to do if we're at this part of the heating curve is we're going to have to use the heat of fusion, or this number right here, which is 6.008 kilojoules per mole. But I'm in grams. So my first step is to get the grams of water and convert the grams of water into moles of water, and I'm using the molar mass. So I add up 1 oxygen and 2 hydrogens, 18 grams per mole, and then I'm going to convert the moles of water into energy because I have the heat of fusion, okay? It's equal to 6.008 kilojoules per mole. So I'm going to put in here 6.008 kilojoules per mole. So if I give out my calculator and I take 15 divided by 18 and multiply it by 6.008 kilojoules, okay, I'm going to get an answer of 5.01 kilojoules, because the grams are going to cancel out, the moles are going to cancel out, and I'm going to be left with kilojoules, okay? So I would be required, like if I had some ice, okay, and I want to change that ice, okay, over to a liquid, okay, liquid water, I would have to add 5.01 kilojoules worth of energy to melt the ice into liquid water. Now, if I want to take that liquid water, okay, and turn it to ice, I would have to remove, okay, so that would be a negative 5.01 kilojoules of energy, okay? Because when it comes to enthalpy, the reverse reaction is equal in magnitude, but opposite in sign. So if I'm melting, I got to add. If I'm freezing, I would have to subtract, okay? So that's how the heat, this problem right here, the heat of fusion, that's how you would work this portion of the heating curve, okay? Let's talk about working this portion of the heating curve before we put everything back together, okay? So let me erase this, okay? this marker sticks very good to my whiteboard here. So the second problem is going to be something like this, okay? What if I have some liquid water, okay? So here's my liquid water, and I wanted to turn that liquid water into some steam. Okay, so as far as a chemical reaction is going to be concerned, it'd be like taking liquid water and trying to get it into a gas, okay? This time I have 25 grams of it, and I am at 100 degrees Celsius. So I'm basically at this point on the heating curve, and I'm trying to get to this point. I'm trying to take my liquid water and turn it into a gas, okay? Once again, we're going to use the heat of vaporization. And in the heat of vaporization is 40.67 kilojoules, but it's on a per mole basis, and I'm in grams. So same thing as before. I'm going to take my grams of water, and I'm going to convert my grams of water into moles of water. And then my moles of water into kilojoules of energy, okay? It's still 18 grams per mole, but now I'm talking about the heat of vaporization. So it's going to be the 40.67 number. So 40.67 kilojoules per mole, okay? And when I take 25 and divide it by 18 and multiply it by 40.67, I find out that I need 56.5 kilojoules of energy that I would have to add in here. I would have to add 56.5 kilojoules of energy to turn the liquid water into a gas. Now, if I want to turn the gas back into the liquid, I would have to pull out or a negative 56.5 kilojoules of energy to turn the gas back into the liquid. So if I'm going this direction, I'm removing heat, so I got to remove it, so it's a negative number. But if I'm going in this direction, I am adding heat. Okay, so as we move to the right, we're adding, and as we move to the left, it should be a negative number. So let's get into our big problem. Okay, this is the last problem of the video, and it's going to include all parts of the heating curve. So we're going to start out with some ice that is very, very cold, like below 0 degrees Celsius, and then we're going to heat it up to steam, okay, to a temperature that's above 100 degrees Celsius, okay? So the problem will work something like this, okay? So got the right page, okay, got it now, okay? So let's say we have a block of ice, and this block of ice weighs 55 grams, and it's at a temperature of negative 15 degrees Celsius. And I want to turn it into steam, okay? So that's my thing for steam. I'll even label it. And it's still going to be 55 grams because we didn't lose any mass, okay? But I want to get this steam to a temperature of 140 degrees Celsius, okay? There's going to be 5 parts to this problem. Number one, and I'm going to put the actual temperatures in here. So we're going to start out at negative 15, and we're going to go all the way up to 140, okay? So there's going to be 5 parts. We're going to have to heat up the ice to its melting point. We're then going to have to melt it, okay? That's going to be the second part. We're going to heat it up to 100 degrees. That's the third part. We're going to vaporize it. That's going to be the fourth part, okay? And then we're going to heat it up to its final temperature of 140 degrees. So when we're in the slope part, remember we're using Q equals MC delta T. And then when we're in the horizontal part, we're going to be using this heat of fusion and heat of vaporization, just like the 2 problems that we did initially, okay? So let's go ahead and get started with the first part. The first part is that we're going to heat up the water to the freezing point. So we're going to use Q equals MC delta T, and we're going to go from negative 15 to 0. So negative 15 to 0, okay? The mass of the water is 55 grams. The specific heat of ice is 2.092, and that's in the joule unit. And the change of temperature to go from negative 15 to 0, remember it's final minus initial, so 0 minus a negative 15, that's an increase of 15 degrees Celsius. So the degrees Celsius cancels out, the grams cancel out, and I'm going to be left with a certain amount of joules, okay? And this comes out to 1,726 joules, which is equal to 1.726 kilojoules. And I'm going to tell you why we got to kilojoules after we do the second part, okay? The second part is we're going to take the ice and we're going to melt it, okay? So this next part is kind of the melting. We're just changing it from a solid to a liquid. So from here to here on the heating curve, okay? Now we have 55 grams, and we're going to convert those grams into moles by using the molar mass. And then we're going to convert the moles into energy using the heat of fusion because we're melting. Okay, so 6.008 kilojoules per mole. So 55 divided by 18 times 6.08, okay, will tell us that we get 18.36 kilojoules of energy. So that's the part two. So part one, part two, and now we're going to melt it. Now, the reason I put this one in kilojoules is because I knew I was going to get kilojoules in part two, okay? So whenever I get done with these sloped lines, because they're in a joule unit, I'm going to switch it over to kilojoules because in the end, we're going to be adding everything together. And when you add things together, they have to be in the same unit, okay? So part three is going to take my water that is now melted, it's now liquid, and I'm going to heat it up to the boiling point. So going from 0 to 100 degrees Celsius is what we're doing, and we're going to use Q equals MC delta T, and we're going from 0 to 100 degrees Celsius in this part of the problem. So my mass is still 55 grams. My specific heat is now liquid water, so it's going to be 4.184 joules per gram degree Celsius. And I'm going from 0 to 100, so 100 minus 0, final minus initial, tells us we got 100 degrees Celsius. The degrees Celsius cancels out, the grams cancel out. I'm going to be left with joules, okay? And when I do that, I get 23,012 joules. Of course, I want that into kilojoules like everything else. So I'm going to divide by 1,000. So this comes out to be 23.0 kilojoules for part three. So right now I'm at this point in the heating curve, and now I'm going to vaporize it, okay? So I'm going to turn things into a gas because we're going to vaporize the water, okay? So we're going to change it from a liquid to a solid. So when we're melting, we were going solid to liquid, and now we're going from liquid to gas, okay? And to do that, okay, we're going to take our 55 grams of water, we're going to convert it to moles, and this time we're going to use the heat of vaporization, which is 40.67 kilojoules per mole. And you can see the grams are going to cancel out, the moles are going to cancel out, and I'm going to be left with kilojoules. So 55 divided by 18 times 40.67, this is going to be the largest number that we come across, and I get around 124.3 kilojoules of energy, okay? So we're at this point in the curve, and the last part is to heat it up to its final temperature of 140. So part 5, we're going to use Q equals MC delta T again because we're on the slope portion of the heating curve. Q equals MC delta T, and we're going from 100 to 140 degrees Celsius for this last part, okay? So the mass is still 55 grams. The specific heat of steam is 1.841, and that's joules per gram degree Celsius. And my change in temperature, the delta T, remember, final minus initial, so 140 minus 100 is going to be 40 degrees Celsius, okay? And when I multiply these three numbers together, I get 4,050 joules. Now, I want that in kilojoules, so I got to divide by 1,000, so approximately 4.05 kilojoules, okay? And I would take these kilojoules, I would take all the kilojoules and add them together, and that's going to tell me the enthalpy change that was required to melt to change 55 grams of ice at negative 15 degrees into steam at 140. And that comes out to be, so 3 sig figs, it comes out to be 171 kilojoules, okay? If you were able to do a problem like this, it means that you understand every single portion of the heating curve. And that's what's going to make you a pro when dealing with these types of calorimetry problems or these thermodynamic problems that you might get where you need to use parts of the heating curve, because not every single problem is going to require to use all 5 parts. You might only have to use 2 or 3 or maybe 4 parts of the heating curve to answer your question. If you found this content helpful, please give it a like and subscribe. And even adding a little comment at the end really pushes this information out to other students that might be interested in learning chemistry.